So now that we've introduced matrix multiplication, let's just do some practice. And I'm going to also illustrate how I would like to see your work as you're doing the problem. So I've got these two matrices, matrix A and matrix B, both happen to be 2 by 2 matrices. I'm going to try to keep them simple so that they don't take too long. And I want to figure out the matrix multiplication A times B, and then the matrix multiplication B times A. And they will not be the same. So now let's start with A times B. Well, so A times B is the matrix 1, 2, 3, 4 times the matrix 5, 6, 7, 8. And what I'm going to do is I'm going to create a new matrix. Now this was a 2 by 2. And this was a 2 by 2. So since the inner dimensions match, the outer dimensions become the dimensions of the new matrix. So it's also a 2 by 2. And what I'm going to do is I'm going to separate it out like this. Give myself enough space to do the computations into this 2 by 2. All right, so the first entry, the first row, column row, is going to be 1 times 5 plus 2 times 7. So I want to see 1 times 5 plus 2 times 7. And then the first row, second column entry will be first row, second column, 1 times 6 plus 2 times 8. And now the second row, first column entry will be second row, first column, 3 times 5 plus 4 times 7. And then the second row, second column will be second row times second column, 3 times 6 plus 4 times 8. And so that shows your steps along the way, what mathematics you did to calculate this particular matrix multiplication. And then, of course, you can show me your final answer. So that's going to be 19, 22, 43, and finally 50. And so that's the final answer. Now, again, I don't need to see this. You should be doing this in your head anyway, just making sure the dimensions match correctly, that the inner dimensions are the same, and the new matrix has the dimensions of the outer dimensions. And then I want you to either draw solid lines or dotted lines and separate out the different calculations that you do in order to show your work, so I know you didn't just let the calculator do this for you, because the calculator will do matrix multiplication, but I want to see that you know how to do it by hand. So now let's do B times A. So to do B times A, that reverses the order. So B times A is going to equal, well, first I'm going to do the 5, 6, 7, 8 matrix, and then times the 1, 2, 3, 4 matrix. And again, I'm going to create another new 2 by 2 matrix with dotted lines to separate out the work. And so the first row, first column, that's first row, first column, will be 5 times 1 plus 6 times 3. And then the first row, second column, that's that one, will be first row, second column, so 5 times 2 plus 6 times 4. And then the second row, first column will be second row, first column, 7 times 1 plus 8 times 3. And the second row, second column, the only one left is second row, second column, 7 times 2 plus 8 times 4. And again, I want to see this work. And then you can do the computations and end up with 23, 34, 31, and 46. And you can see that this matrix and this matrix have nothing to do with each other. These are very different matrices. So A times B and B times A are generally not going to be equal to each other. So keep that in mind. Matrix multiplication is not commutative. So matrix multiplication is not commutative. That's the property where you can switch them out. switch the order, and you get the same answer. So the matrix multiplication does not work that way. So here's some more examples. Here's matrix P, which is a 2 by 2. Here's matrix Q, which is a 2 by 1. So if I want to do matrix P times Q, so PQ is going to equal 1, 3, negative 1, 2 times 5, 2 as a column matrix. Well, this one was a 2 by 2, and this was a 2 by 1. So the inner dimensions do match. The 2's on the inside match. So the final answer is going to be a 2 by 1. Now, since it's so small, if you don't want to draw the little line in the middle, you don't have to. I'm going to do it anyway. But you don't really have to because there's only 2 entries in this whole thing. So the first row, first column entry would be first row, first column. So 1 times 5 plus 3 times 2. And the second row, first column be second row times first column. So negative 1 times 5 plus 2 times 2. And I do want to see that work again. I don't need to see this, but I do need to see this to know that you understood how to do the calculation. And so that's going to be 5 plus 6, which is 11, and negative 5 plus 4, which is negative 1. So that's 11, negative 1. Now, if I want to do QP, well, QP is going to be 5, 2 matrix times 1, 3, negative 1, 2 matrix. This is a 2 by 1 matrix, and this is a 2 by 2. Oh, wait a minute. These dimensions do not match. In fact, I probably could have seen that from the beginning. I didn't really need to write this down. So this is just impossible. There is no product here, Q times P. So P times Q works, Q times P does not work. Yet another example of why matrix multiplication is not commutative. Okay, so I've got this matrix A, which I'm actually just going to use variables A, B, C, D. And I've got this matrix which is called I, which is 1, 0, 0, 1. Let's do A times I. Okay, so A times I is going to be A, B, C, D times 1, 0, 0, 1. So this was a 2 by 2. This was a 2 by 2. The inner dimensions matched, so that's good. So the final answer will be another 2 by 2. So let's separate it out, give myself space to do my calculations. Okay, so the first row, first column entry will be first row times first column. A times 1 plus B times 0. And then the first row, second column, first row times second column, A times 0 plus B times 1. And then the second row, first column would be C times 1 plus D times 0. And then the second row, second column would be C times 0 plus D times 1. And when you simplify that, you end up with A, B, C, D, which was the original A matrix. So I have basically done nothing by multiplying A times the I matrix. I just got the A matrix back. All right, let's try doing I times the A. Let's do that in reverse. So that's going to be 1, 0, 0, 1 times the A, B, C, D. And again, it's a 2 by 2 times another 2 by 2, and the inner dimensions match, so the final answer is going to be another 2 by 2. Okay, so the first row, first column will be 1 times A plus 0 times C. The first row, second column will be 1 times B plus 0 times D. The second row, first column, will be 0 times A plus 1 times C. And the second row, second column, will be 0 times B plus 1 times D. And when I simplify that, I get A, B, C, D. Once again, I get my A matrix back. So A times I was equal to A. and I times A was equal to A. So I is a special matrix. I multiplied matrix A by the matrix I, and I got my matrix A back. It actually has a name, which we're going to talk about in the next slide. So this matrix I is known as the identity matrix. Now, depending on the dimensions, there's different versions of I, just like there are different versions of the zero matrix based on the dimensions you needed. However, the identity matrix is always going to be a square matrix. In other words, it'll have the same number of rows as it has columns. So it'll be n by n, like 2 by 2, 3 by 3, 4 by 4. The way you create the identity matrix is you basically have a whole bunch of ones down what is called the main diagonal. So this diagonal here is called the main diagonal. And then the lower left triangle is made up of zeros, and the upper right triangle is made up of zeros. So you have ones down the main diagonal and a bunch of zeros on the remaining entries. So the 2 by 2 would be 1, 0, 0, 1, because those are the main diagonal and those are the only two zeros left over. The 3 by 3 identity is a bunch of ones down the main diagonal and then 6 zeros, 3 on each side. The 4 by 4 identity has 4 ones down the main diagonal and then 6 zeros on either lower left triangle or upper right triangle. Now the identity, we've heard of an identity before with real numbers. So with real numbers, the multiplicative identity is what we called it. Is the number 1. And the reason is that 1 is called a multiplicative identity, it's because if you take 1 and you multiply it by x, by anything, you just get your x back, right? So you multiply anything by 1 and it doesn't change the value of that thing, that real number. So the identity matrix, the I matrix, does the same thing. You do a matrix multiplication of the appropriate order, and you get your other matrix back. So A times I or I times A is just going to give you your A back. So the identity matrix acts just like the number 1 did in real numbers, except now it's a matrix. And that's the end of the lesson.